We are very happy to invite Dr. Laura Alvarez to give a talk on Minitalk. Laura comes from ETH Zurich, and he is working with Professor Lucio Isa. He will talk about the reconfigurable artificial microswimmers with the internal feedback. So let's welcome Laura to share her research.
Right. Thank you so much for the introduction, and thanks, Professor Wan, for the invitation. It's a nice initiative. As you said, I will present in the work that we recently published, also not so long ago, a couple of months ago, in ETH Communications about what we believe is a new type of artificial microswimmers. And I hope that by the end of the talk, you can understand when this video here that I'm showing. So I believe that most of the people working on artificial microswimmers or nanomotors, microrobots, we find our inspiration in biological microswimmers. And here I'm showing you this nice animation of E. coli. This here in the center is supposed to be a sugar crystal that is dissolving. And as many of you might know already, bacteria, in this particular case E. coli, they're able to interact with environments in order to adapt their behavior. In this case, they perform chemotaxis, so they swim towards high concentration food regions. And this is basically possible due to their very, very complex machinery that nature has given them. But at the end of the day, all comes down to their ability to interact with environment, sense the stimuli, and adapt their dynamics. So the question is, how can we imitate this type of biological microswimmers, this perfection coming from nature? We know that, I mean, I already spoiled, like most of the people working with micro robots will try to build these micro robots or artificial microswimmers. And maybe the first image that comes to your mind, or at least in my mind, I always imagine this picture, this very nice scheme or idea that Isaac Asimov, a writer, sci-fi writer from the 60s, that he imagined these micro robots that will go into bloodstream as a very small starship. You can imagine already that this won't be possible with our experimental resolution right now, maybe in the very, very far future. But it's indeed true that what we can do is use a much simple units in order to engineer this type of swimming that mimics biological microswimmers. And at the end of the day, what we also want to do is try to scale down some functionalities like sensing and responsive behavior, and obviously engineer motion at low Reynolds numbers regime, which means that we have high viscosities. Now, the systems that we use, or the very simple building blocks that we use to try to reproduce biological microswimmers behavior, are active colloids. And active colloidal particles, I'm sure most of you know, are just colloidal particles in the nano or micro scale, but they're able to harvest energy from the environment and transform it into propulsion. Here I'm showing you just a very known video of a Janus particle. So this is possible because they are asymmetric in shape or composition. Now, there is many ways to actuate this type of particles, this type of colloidal particles. Most of you might know already the very studied case of Janus catalytic particles, that they are able to catalyze the discomposition of hydrogen peroxide thanks to their platinum hemisphere. And although the mechanism of this is not clear and is still under debate, we know that because of this asymmetry, this particle propels in the direction of the non-platinum cap. Now, apart from the power fuel particles, active colloids, we also have another types of actuation mechanisms, like, for example, external fields. And here I will come back to the details later, because this is a main mechanism that we use. But just long story short, what we have here is, again, a particle that is a symmetry in shape and composition in this case. And by applying an AC electric field that is perpendicular to the plane, we have a different polarization of the charges around each particle, and basically this translates into net propulsion. So people have looked into different propulsion mechanisms, but also the different types of shapes that we can build, and even tasks. So, for example, here I'm showing you the very characteristic type of motion for L shapes, this circular motion, that it's very distinct from, for example, only a sphere, a Janus particle. And this is something that the shape and color dynamics is something that people are trying also to explore and understand. And also, for example, people are trying to perform or fabricate, engineer some sort of simple task of these microswimmers, as for example, this cargo release of this Janus particle that is able to trap these bits in solution and just release them. Well, I don't have to motivate why they're so important and interesting, the systems. First of all, they serve as a model system for out of equilibrium dynamics, as for example, collective behavior that we can find in nature or even in colloidal systems. They can be used also in bottom-up synthetic biological approaches, like for example, using as non-living material units. And last but not least, right now it's kind of a hot topic. We can also use them, and this is one of the main applications in biomedical applications, for example, for cargo release or a very punctual treatment. Now, I show you right now these examples here, and there's other many, but something that I think we believe is still quite limited in comparison with biological microswimmers is the fact that these particles are still limited in the way they sense and adapt to the environment. And I think that one of the main challenges right now in the active matter community is to work towards some sort of autonomous artificial microswimmer, somehow that has different degrees of freedom and autonomy, and we can basically at some point reproduce what we see in nature. So the challenge is this, to start giving autonomy or at least adaptive behavior to the particles. So the way we have addressed this is by incorporating responsive materials to active particles or building active particles with responsive materials. So what you're seeing here is a scheme of our active colloidal particles, which is basically a polystyrene bit that has attached a polynipam microgel. And for those who are not familiar with these microgels, polynipam is basically a polymer that has a volume phase transition above 32 degrees, which means that in water, when the temperature increases about this value, it shrinks in size, and basically it can decrease in size up to 50%. So what we do here is basically trying to reconfigure this particle, this colloidal assembly that we have by illuminating with light, and with the right amount intensity of light, we can actually increase the temperature above this phase transition point and make this particle shrink. And I hope that you can see here in this video. So this is a microscopy video of the polystyrene, which by the way, is fluorescent. And here I hope you can see the blob, which is the microgel. And by switching on the lights with the right intensity going above this phase transition point, we have this reconfigurable system that, as you can see here. So yeah, I mean, this was pretty cool that we actually have this reconfigurable system. Obviously, we are controlling light temperature with light, but you can also imagine that this will happen organically in a bath, in a bath by just a change of temperature on the ambience. So the question is now, well, are these particles active? Well, I can tell you that they are already, and the way that we actuated them is by squeezing this colloidal suspension of these dumbbells in between two conductive electrodes, and we apply an AC electric field. So the mechanism behind here, and maybe we can discuss this afterwards in the questions, is that basically we have two particles with different dielectric properties, with different ion clouds and different polarizability, conductivity of these ion clouds, right? So by applying an AC electric field, as I said before, perpendicular to the plane, what we are doing with a given frequency, what we are doing is polarizing these charges around each particle. And depending on these polarization properties, basically, we will start distorting the fluid flows around the fluid around the particles, creating these fluid flows that are not the same. And depending on the magnitude and sign, as I will show later, provokes that this particle move. So what I'm showing you here now is a video of this sample. So basically, you have to imagine that most of them are dumbbells. We will only see the fluorescent polystyrene due to for tracking reasons. So right now, what you're seeing is just this active colloidal particles swimming with their intrinsic velocity and rotational diffusivity for a dumbbell at low temperature. So basically, the microgel is big right now. And at some point, I will increase the light intensity, the temperature will increase, and then I hope you can see that the dynamics drastically change. Finally, this process is reversible. So if I go back to the initial conditions of light, so the temperature basically equilibrates again to room temperature, we basically recover the same dynamic speed behavior that we had before. Here I'm showing you qualitatively basically the type of trajectories that I'm showing in this video. So the blue part of the trajectory is a low temperature, how these particles swim at low temperature, and the red part of the trajectories are these when we increase the light intensity and therefore the temperature. So you can see that we have, these particles are actually able to adapt to this temperature change and change their persistent length. Here, I'm also showing the velocity of these particles as a function of time for different types of illumination intensities. Typically, these particles swim with around 5 micrometers per second at room temperature. And when we increase the light intensity, you can see that this drops almost twofold. But when we turn off the light and the temperature decreases, so basically this swelling transition goes back to the initial state, these velocities are recovered. And I hope you can see also that this has a given delay time. I won't get into the details of this, but I can tell you already that depending on how these microgels shrink or swell, this can be tuned by the way we synthesize them. These delay times can be tuned. So this is very interesting because I would like to remark that the change of dynamic behavior is not due to a change on the electric field. The electric field is always constant, but what happens here is the particle has this small sensor that tells the particle, okay, now it's warm, so the microgel shrinks and then the dynamics basically change. So something that we actually didn't expect or didn't see from the previous video is what we saw when we were going higher in higher magnifications, is that these particles not only decrease their velocity, they also increase a bit the rotational diffusivity, by the way, I didn't mention before. But what happens also is that they change the direction of motion. So when at low temperatures, when the microgel has this big state, this particle swims with the polystyrene lobe in front, okay? Now, when we increase the temperature, we're increasing the light intensity, what happens? So again, this shrinks, but then we also see that the particle changes direction, the direction speed. So I'm showing you here a video and I hope you can really see it. This particle over here that I'm showing with my cursor. So the big dark lobe, it is a polystyrene, and this is small, I hope you can see, a very small whitish blob is the microgel. So at low temperature, the polystyrene swims in front. I switch on the light, high intensity of light, this temperature increases. And now at some point, the direction will change. I will focus again. And then here, I hope you can see that the particle basically swims with this very, very tiny, small whitish blob. And when I switch off the lights, the initial direction is recovered. So we quantify all of these events. And indeed, what we saw is that there is a consistent change of direction when we increase the temperature. And not only the direction changes, but we have also a twofold decrease of the velocity of these particles. Now, at the beginning, when we saw that, we really thought very naively that the reason behind this each was just like a size change of this microgel, right? There is a theoretical model from people in the University of Colorado that have explained also the swimming behavior of these tumbles, and it depends on the size of the different particles, and well, also on the different properties, the electric properties. But at the beginning, we just thought, okay, it's just like the size change. However, when trying to fit in this model, with this only size change, nothing worked. And in order to explain that, actually, we had to go back and try to understand the electric properties of our system. Because as I said before, when we actuate these particles under electric field, what we are doing is polarizing this this charge cloud that the particles have. And then therefore we need to have access to the properties of this particle, the electric properties. Here, what we did basically is measure the electric properties, which means we measure the conductivity of the particle, and also the polarizability of the particle, and also the polarizability conductivity of the media, to get what we call the polarizability coefficient or Clausius osmoticity factor, which basically describes the polarizability of the particle with respect to the media. Now, why is this important? Because actually, the way we can explain motion of these two particles together is by understanding what's happening around them, right? So as I explained before, when we apply electric field perpendicular to the plane, and if we have the particle close to the substrate, these electrohydrodynamic flows are created, and they have a given sign and a given magnitude. And you can imagine already that if you have two different particles, the combination of these two particles together plus their flows will be given these different types of behavior. So as you can see here, this is the expression that describes the velocity of these flows at a given distance for a particle. And here, basically, big R is the radius of this particle, that for the microgel, it's depending on temperature. R small is the radius of this particle plus a distance, which we will consider will be the center of the particle when a dumbbell is formed. And as you can see here, also, we have the components of the Clausius-Mosity factor, so the real and imaginary part. And these are very important because they will actually tell you, they will define the sign of these flows. And finally, once we have the velocities of these flows around the microgel and the polystyrene, we can plug it into this first order approximation in which we consider the radius of the particle and the velocity of these flows of the other particle. And then we can basically try to recover the velocities that we are observing experimentally. So this is just to show you how this type of properties behave. So this basically, we measure this in a group in Spain, in San Sebastian, where they can actually measure the electric properties of colloidal suspension. So we measure the properties, we would calculate the Clausius-Mosity factor, the real and imaginary part for the polystyrene, which is the pink data, and the gray data for the microgel. And we represent this as a function of temperature because this is what we are observing. So as you can see, for the real part of the Clausius-Mosity factor, we don't have such a big change for the polystyrene as well as for the imaginary part. But when we go to the microgel, we actually have a change, a different change, quite a bigger change in the real part. But the most important is also in the imaginary part, which basically it changed its sign for something that it's positive to actually negative. So then when we plug in these quantities plus other, like for example, as explained before, size and viscosity of water in this expression, what we can calculate is how these flows behave around each of the particles individually. So again, the pink data, so this is basically the electrodynamic flows of one particle as a function of temperature. The pink data represents the flows around the polystyrene at a distance that is described by the size of the microgel that is close to it. And I mean, nothing really important happens, maybe just at the end. So at higher temperatures increases a little bit because also viscosity of water, which is here, decreases. Now, in the case of the microgel, as you can see already here, we do have a very important change. And the important change is basically that we have a sign change. So when we have values that are positive, and this is very well described in this paper from Fuyoma, and these people are in the University of Colorado, and they are specialists in this type of systems. So basically what we have here are flows around the particle that are extensile, or what we call also repulsive. So basically these flows, you have to mind that they go this direction. And when they're negative, we do have the other case. So these are retractile or attractive. So now that we have this data, we can use this first order approximation, and then we can calculate the total velocity of our dumbbells. And here I'm showing you basically the velocity of our dumbbells as a function of temperature. The symbols are the experimental data points, and the solid line is the theoretical calculation that I just explained to you. So we rationalize this as an effect combination of these two types of hydrodynamic flows. So at lower temperatures before the phase transition of this particle, which as you can see here is around 32, we do have a predominant fluid flow that comes from the microgel. So basically, the magnitude, it's much bigger on the side of the microgel than the side of the polystyrene, and therefore this particle is pushed towards the polystyrene lobe, and that's what we observe experimentally. When we increase temperature and then the microgel decreases size, we do have an inversion of this flow, and also the magnitude decreases. And therefore what happens is, by combination of these two types of flow, we do have an inversion of the swimming velocity, and also a slight decrease of the swimming velocity. So I mean, this is pretty interesting because you can already imagine that this is not only about shape, but it also depends quite a lot on this electric properties variation. So this actually opens up a really, really nice door to start exploring other types of responsive materials, especially microgels, because microgels can be synthesized in different ways. So we can basically tune the swelling ratio, we can tune the surface charges. And all of these will determine the way they respond to, for example, temperature. So this is pretty cool, and it opens up a spectrum of other type of behaviors that we can start exploring. So after this very dense slide, I would like to show the very last results, and I think they're very graphic and beautiful. One of the things that we can also do with these particles is to basically have a spatial control of on a spatial control of these microswimmers. And actually this part of the work was very much inspired by also people in Italy that have worked with light-activated bacteria, and they are actually, well, it's the opposite effect actually, but they are actually able to localize bacteria with some sort of shapes. So what you're seeing here is experimental data trajectories, and here this dash circle represents the area where I'm illuminating and therefore increasing temperature. And as you can see here, when this happens, since the velocity decreases and the dynamics decreases in general, we do have an effective accumulation of particles in this area that actually relaxes back when we switch off the light. And these cycles, as you can see here, I mean, this can be done multiple times. Finally, up to now, I have been talking only about dumbbells, but we can also explore other types of shapes. So here, I hope you remember at the beginning that I also mentioned these L shapes. So here what we do have is a L shape that is composed by two polystyrenes that are attached together. And this small blob over here is the microgel, the polynitride microgel. So because of the shape and asymmetry of this type of particle, and the fact that the force is coming from the combination of these two, and then we have an effect of the second here that causes a drag and therefore torque, we do have the circular motion. And at low temperatures, we do have a very distinct circular motion with a rather small radius. But when we increase the temperature, this radius increases. But I hope that you can see that it's not only about the radius, but also we do have an inversion of the chirality of this type of circular motion. And again, this basically happens because, as I explained before for the dumbbells, at low temperatures, the force is in this direction, and when we increase the temperature, the force that basically actuates the particle and makes it swim basically changes to that direction. And this actually is pretty cool because it's also reminiscent to some sort of biological swimmers that are able to swim in this circular motion close to a surface. So with this, well, and this is just to basically highlight that we can actually have a spatial and kinetic control and adaptability of these particles. So with this, I would like to go to my conclusions and outlook. First of all, I hope I convince you that we have designed and fabricated a system that kind of try to follow the sense, stimuli, and adaptation that I showed at the beginning for bacteria. In this case, we use light to create a change of temperature, and because of the incorporation of this new material, we do have a reconfiguration that translates in a dynamical response. We believe also that the incorporation of responsive materials are crucial in order to have adaptive microswimmers in general. In this particular case, it's very important to highlight that we decouple the propulsion mechanism, which is the AC field, from the responsive behavior, which is only intrinsic to the microgel and the particle properties. So in this intrinsic adaptation, there is no external intervention, as in there is nobody that is basically changing this electric field or changing the propulsion mechanism. So other things that might be, they are able to be done with this type of system. So these microgels are also pH responsive. So the way they change the swell or the shrink, it can be also pH dependent. So you can already imagine how this can be used. We can also explore these guys under chemical gradients, and even we're looking now into the collective behavior. And finally, we're now exploring other types of shapes. For example, these trimers or triangles that this has been doing by our brilliant student, Steven Bankensterian. Also, we hope soon we will publish another paper on this, so heads up for that. And yeah, so for this, I would like to finish now with the acknowledgements. This wouldn't have been possible if Lucio Isa wouldn't have given me this opportunity to work in this exciting project. I really fell in love with active matter, and obviously all my group, very nice ambience and workflow. Very important here also our collaborators in Spain, Professor Ángel Alegría and Silvia Rese Igor, which basically help us a lot to understand do the measurements of the electrical properties and understand also how to analyze this data. Professor Martin Kruger in ETH, Dr. Miguel Ángel Fernández Rodríguez, now in the University of Granada. And of course, all the funding mechanisms, especially I would like to highlight EUSMI, which is a European network. And thanks for your attention. I will really be glad to take questions.
Okay, thank you, Laura. Thank you for your last talk. And let's see if we have question or comment from the audience. Please feel free to unmute yourself and ask us questions.
Hey, hello.
Yeah, hello.
So very nice talk. I just wonder how fast temperature-sensitive polymers will respond to the irradiation. So will the irradiation heat up the whole solution or just heat up the local at the colloids?
Yeah, that's a good. Thanks for the question. That's a very nice question and very important here. Yeah, I forgot to mention. Let me go out from this. Yeah, so basically, at the very beginning, we thought that we were heating up, because these slides are covered with gold, copper and gold. So at the very beginning, we thought that this was being heated up as a general, like the whole bath, or we were eliminating. But later, when we started to look into diffusion coefficients, we actually observe that it's not only about it doesn't heat globally. It is a combination of a slight heat that happens globally because we are illuminating and gold absorbs, but actually there is an effect that happens locally on the polystyrene particle, and we are now trying to understand this mechanism, because if this is true, this means that basically nobody has looked into this. So we are trying to understand why this happens, and if it's just a combination of the mean bath of the increase of the temperature basal temperature of our bath, plus this slight increase on the local level. But yeah, indeed. So this basically happens on a local level, and we haven't observed that for particles that haven't been illuminated, basically. And this is one of the actually nice features of the system.
Mm-hmm. Thank you.
Any other question?